Finishing Turborepo's migration from Go to Rust. This is going to be a fun one, guys, because Turborepo is a JavaScript toolchain that was originally written in Go, is now written in Rust, and used Zig as a tool to get there. This experience has been nuts. This is not the first blog post about it. In fact, we'll be referencing the other ones throughout. I know I'm not the Go or Rust guy, but I do think I have a lot of unique context here because I know a ton about the history of Turborepo as well as how it's used. Even if I don't fully understand the language of Rust and I pretend to understand the language of Go, I understand what the goals are here. So this will be fun, especially with my recent spicy take that Rust is probably not the right tool for a lot of JavaScript developer tools. I think the language we pick for these things matters more than it ever has before, but yeah, here in particular is going to be fun. So, we finished porting Turborepo, the high-performance JavaScript and TypeScript build system, from Go to Rust. This lays the groundwork for better performance, improved stability, and powerful new features. It's interesting to call Turborepo a JavaScript and TypeScript build system. It's more a repo management tool, but we'll see where this goes. Gotta love the Acme references. For those that don't know, Acme's like the default company or big example thing that people use as a name for template projects and shit. So fun to see them fully committed to that. Also funny that the site is in Next, the dashboard's in Svelte, and posts, or their blog, is in Nuxt as the example, fully embracing other frameworks and even their placeholder images. Here's how we finished this port and shipped the first all Rust version of Turbo. Since the last time, at the end of our previous post, we had completed the Rust Go Rust sandwich, or Go sandwich for short, and shipped it with some help from Zig. The sandwich allowed us to keep incrementally porting pieces of Turborepo. Since then, we've ported more components, such as the file hashing, which is Turborepo's mechanism for creating a fingerprint of the content in your repo to make cache comparisons fast. This is really important if you're not familiar with Turbo. What this effectively lets happen is if you have a package inside of your monorepo that none of the files have changed in, and none of its dependency packages files have changed either, then you can skip running the build step and just give you the cached output. A huge part of why Turborepo is so cool is the amount of time that gets saved by those optimizations. So here is the amount of compute saved. This isn't just like server compute. This is specifically the experience that individual devs have had saving time on their machines. That's 2 million hours saved. For comparison, here is the life of my channel. We've had 2.6 million watch hours total. There are little days they missed, but none of those are relevant for me because I only started posting in like April of 2022 for real. So like, yeah, 2.6 million watch hours on a channel that's pretty big, almost 30 million views, 2.3 million hours saved. There has been roughly as much time spent watching my videos as Turborepo has saved in time running builds on your computer. That's a pretty cool metric. But of course, in order to actually do that, you have to check the files and make sure the hashes are not different, because if they are, you have to rerun the steps. So doing that check quickly and efficiently is a fun challenge that they've rewritten in Rust. It's actually kind of funny. This is one of the final things they rewrote in Rust that was in Go originally. We'll talk about why in a bit. They also mentioned the lock file analysis, which is checking the dependencies in your repository so that Turbo can account for that, as well as cache signature verification in order to make sure the cache that you're running and downloading locally is the same as the one you posted in the past, which you can do by adding your own private keys to hash those checks. Cool stuff. And also nice to see all of this is in Rust. I want to touch a little bit on the Zig incremental piece here because it is very, very interesting. First off, because they have to compile to 6 different platforms. Just for reference of the hell this team is going through, there's a section dedicated to Windows ARM because the actual things that Windows ARM supports are so limited that they didn't know which ones would or wouldn't actually work. And what they ended up learning is that Go's use of MinGW conflicted with Rust's use of MSVC on ARM, and because of that, they couldn't link the languages together. The solution was to use Windows' built-in x86-64 emulation, which, if you've ever used this on an ARM Windows computer, you know it's nothing compared to Rosetta on Mac. It's shit. And they had to do this and eat a massive potential performance issue in order to get this hybrid solution working, which means that Windows ARM users probably had much worse performance overall as they were porting over to Rust. The final result might be slightly better, but in the interim, utter insanity and hacks. And this utter chaos is why something like Zig had to come in. Specifically, Zig's compiler, the Zig CC, which is not an ordinary C compiler. It's a C compiler that is easy out-of-the-box support for cross-compilation. It also has crazy comp time stuff where you can have the compiler generate dynamic code as you're compiling, which unlocks insane amounts of cool features and functionality. But the point here is the cross-compilation enabled a lot of the specific behaviors they wanted to implement on these different platforms. They call it here, cross-compilation in C is quite painful, requiring installing a compiler for a specific target or building it from source, finding versions of libraries for that target platform, and writing a lot of compiler flag magic. Erasing all of these concerns practically made us jump with joy. ZigCC even comes with a nice long list of targets that it handles out of the box, with bundled libraries, including, you guessed it, all of the targets they needed to build. There was some skepticism. How would we use Zig and Go and Rust? Would that just be too much programmer hipsterdom? Would Hacker News and developer Twitter judge us too harshly? Who cares about them? We're talking about my audience. Let them know in the comments how harsh you feel about them combining all of the spicy, hot new languages in the same project as a temporary measure. But yeah, they called out, it worked. They had to do some weird linking stuff in order to get these things bound together. But as a result, they had the ability to build one code base that interfaced with old Go code and new Rust code, with Zig as the compiler glue pulling it all together. Wild stuff. This blog post is particularly nuts if you want to dig into what they're doing and why and all the platforms they have to target. Pretty cool stuff overall, including the breakdown of the Go sandwich. In short, it consists of a Rust binary that calls a Go binary, which in turn calls Rust libraries that are statically linked in the Go binary. So Rust exists outside, calls the Go binary, which then has Rust embedded within it, because there was no easy way to embed Go within Rust. So the Go is in between these two layers. I am happy this isn't my job. So what were the issues? Let's hear the limitations of the Go sandwich. As we completed these components, we started to realize the limit of what the sandwich could handle. For example, mixing asynchronous, multi-threaded code across languages wasn't going to be viable. The Go sandwich got us to this point, but with so much of our new code now moved to Rust, the sandwich had fulfilled its purpose. Therefore, we decided to build what we called the run outline, an all Rust version of our run command, with most of the functionality stubbed out, replaced with a fake simple version. We gated this behind a feature flag so we could build on our local versions but not ship to users just yet. It was the time to complete the switch to all Rust. Building the package graph. The first big piece we added to our run outline was the package graph. The package graph is a graph data structure of all the packages in your Turborepo, where the graph's nodes are your packages and the edges are the dependencies and relationships between them. This allows us to deeply understand your monorepo and cache work, so you never have to do it twice. When we ported the package graph, we noticed that Rust's features allowed us to build better types that more accurately model your repository. Not only does it allow you to do that, it brute forces you to, because Rust is so strict with its types. For example, in Go, we designated the workspace root where your lock file lives with a magic string. Nice little comment. Package names were stored as strings, so to check the workspace root, we checked if the name was equal to the /. In Rust, we were able to model this as an enum. Enums in Rust allow you to create a type that could be one of multiple values. In this case, our package name could be either the root package or a different package with a name. We can model this as root or other string. Interesting. Not only is this more efficient, it also ensures correctness. Whenever a package name is used in the Rust code, we have to handle the workspace root case or the compiler will complain. In Go, it was a lot more tempting to use strings and handle cases in an ad hoc manner, leaving more room for error. Yeah, understandable. The prune command. When the package graph is completed, we are ready to tackle the all Rust version of prune. The prune command lets you remove everything from your Turborepo except a single package and its dependencies. If you run turbo prune web app, you'll create an out folder with only the code and the dependencies for the web application. So if we have these two root level packages, the A and the B, A depends on these things, but not these. But then when you run the prune A command, it will remove all the things that only B needs. This is particularly useful for building Docker images when you'd like to keep the size of your image small. We're also excited about building functionality on top of this command, like using pruned lock files to only install the dependencies for the application that you care about. Fortunately, we've already ported most of the lock file code via the sandwich, so it was just a matter of connecting our existing pieces. If you look at this pull request, we were able to merge prune with relatively little iteration. This is because the Go sandwich had allowed us to build up the Rust dependencies and test them in our existing Go code. Makes sense. Hashing tasks for the run command. Once we completed prune, we reached one of the core pieces of Turbo, hashing. Hashing is what allows Turborepo to determine whether you have to run a task already. Again, this is where all the huge performance wins come from, is knowing whether or not you have to rerun something based on if its inputs have changed or not. In fact, other languages like, Rust could benefit a lot from this because Rust compile times are shit because it recompiles everything always. You can't even install a binary from the crates world. You have to install the source code and then recompile it whenever you want to compile something. And since Rust has so many deep checks in its compilation steps, good luck with the performance on those. In fact, I've heard from many sources, including Vercel themselves, the performance of compiling Next, of compiling Turborepo, of compiling SWC, and all of these other things they're building around has gotten significantly worse as a result of adopting Rust, with the goal being that adoption of Rust slowing them down so it can speed us up as we're just compiling JavaScript in the future. Interesting goals. Regardless, funny to me that Rust is being used to make compile times in JavaScript faster, even though Rust's compile times are utter shit. So, what is hashing? I feel like we know what hashing is, but let's take a read. A hashing algorithm takes some data and produces a single value, known as a hash. With a very high degree of probability, these hashes will be unique to the input data. You end up with a fingerprint of your data that can be quickly compared to other fingerprints. This is advantageous since hashes can be created quickly and are easy to compare against each other. Hashing shows up in a lot of different places, whether it's mapping keys to values in a map, efficiently storing different versions of your code in Git, or safely storing passwords. In the case of Turbo, it's seeing if a file changed or not. They use it to implement their cache. When you use Turbo Run, Turbo takes all of the different inputs that go into building your packages, like source code, environment variables, and dependencies, and sends them through the hashing algorithm. There's also a fun call out if you're not deep in the MONOREPO world and the caching behaviors here. Environment variables are a really, really important piece of how this caching works because a lot of these environment variables get compiled into your code. Like, for example, if you have next public environment variables in a Next app, when you compile that, those next public flagged environment variables end up in the front-end code that your users are downloading and running. So if those change, then your code output has changed too when you run your build step. So if you're only caching based on the code that's input and not the environment variable change, you might download a cached version of this build that has the wrong environment variables baked into it. That said, now if two different team members have slightly different environment variables, you can't share a cache anymore. So it's a fun balancing act that we've learned a lot about. And the result for a while, and I think this is still the case, is that you have to explicitly call out which environment variables don't affect the cache when you're using Turborepo. Anyways, they solve this problem at two levels. First, at the global level, they produce a hash that determines if you've changed something that affects the entire repo. This is for things in like your config, core packages that are being used, global environment variables, stuff like that. And on this other level, they also create many task hashes to determine if you've changed something for a specific task. The global hash is included in calculating these hashes, so it can potentially change all of them. Good to know. To use these hashes for your cache, we store outputs of your task in a tar file, a special file that compresses an entire folder into one file. We store that file in both the local system and in the Vercel remote cache, indexed by the task hash. You can also use your own caches. There's a bunch of documentation on how to cache your remote Turbo stuff yourself, but the Vercel stuff is, I believe, effectively free. It's so cheap, and I just use that. When it comes time to run a task, we first produce the task hash and check if it's in either the file system or the remote cache. If it is, we restore the task's outputs in milliseconds. Otherwise, we run the task and store the outputs in the cache file for next time. Ensuring hash stability while porting run and prune. Oh boy, that's a fun point. If they have to port these things over, they want to make sure the caches from the Go version still work in the Rust version. It doesn't make sense for Turborepo users to miss cache just because the language that was used to write the tool changed under the hood. They had to prioritize stability. To keep hashes stable, we turn to Cap and Proto, a cross-platform, cross-language serialization format that is defined byte for byte. More importantly, though, this library has great support for both Go and Rust, so they could use it in both. After refactoring our hashing code to use Cap and Proto for both Rust and Go, we set up our CI to run our tasks on both code paths and compare the two hashes. If they ever diverged, our CI would fail and we would need to make some fixes. Reaching the finish line. When we started running the hash comparison code, we weren't surprised to find we had bugs. Some were minor, like ensuring null values contributed to the hash correctly. However, some bugs were more foundational, like detecting which packages had changes or handling the filter flag so you only had to do the work you were looking for. We're glad to see our approach pay off here, as these would have been incredibly difficult bugs to find otherwise. In the end, we were able to validate that our Rust hashing code was working and matched the Go behavior, which is importantly has to perfectly exactly match. Overall, this approach really paid off for us. We found a lot of bugs that otherwise we would have struggled to find. We were able to validate our code was working and match the Go behaviors, dogfooding our way to a release. This is something I don't think Vercel gets enough credit for. They dogfood so hard. They're regularly shipping things that are fundamentally broken and just never make it to users because they want to deeply understand all of these things. At this point, we had ported enough code to run our tasks in our own CI behind an experimental Rust code path flag. We began running our integration tests on the Rust code path and burning down the test failures until we matched the Go version, log line for log line, output for output. Once all of the tests were passing, we published a canary version and we used it in Vercel's internal monorepo. Once we reached 72 hours of no errors, we shipped version 1.11 of Turborepo, which is, again, a rewrite, effectively, in a new language. Looking back, this port was a major success. We managed to port 70k lines of Go to Rust in 15 months with minimal disruption to users. Our porting strategies, such as the Rust shim and the Go sandwich, allowed us to incrementally port code for as long as possible. With that said, there were probably a few things we would have done differently with our newfound knowledge, like invest in a single serialization format from the start. Makes sense. Shipping each porting strategy faster. We waited a little too long to figure out our release strategy for the Rust shim and the Go sandwich. This meant that there were times where we had ported code which we could not ship due to release management bugs. If we had shipped an absolutely minimal version of each porting strategy as early as possible, we wouldn't have had these issues. There's other things I'll be talking about. I have so many controversial takes. I just wanted to read through this first and then we'll go into my thoughts. Point 3 here is that we've realized the importance of code quality before porting. By and large, our Go code was in a good state with comprehensive testing and fairly straightforward architecture. However, we came in thinking that we could refactor while porting, but that turned out to not be the case. Looking back, we might have been able to port faster had we improved our testing story and removed some bloat from the Go code before starting. The final point here is they could have fully specified the core Turborepo behaviors like globbing, file watching, and hashing earlier. We discovered many cases during the port where it wasn't clear whether some behavior was accidental or intentional in the Go code. It would have helped to uncover these undocumented and untested scenarios that are now codified in Rust. We also could have solidified our cross-platform support, specifically for our Windows testing. This is a fun one, because if you guys don't know the history of Turbo, Jared Palmer was the main creator and developer for most of Turbo in its early days. When Turborepo got acquired by Vercel, he slowly shifted more in the direction of build tools and then soon after AI. And now Jared runs all the AI stuff at Vercel. I don't think he touches Turbo at all at this point, which is good for him, exciting. They needed someone to do that. But Turbo is now kind of being left to be cleaned up by the new team that's taken it over. There's a lot of reasons why they can and should adopt new tools and technologies that make more sense for them. But part of the pain points here are not knowing which behaviors were actually intentional or not. That's never fun. Having been in that scenario before, not great. The future of Turbo. We're incredibly excited for the future that Rust will bring to Turborepo and TurboPack users. We're finding new opportunities every day to create great features, ensuring improved stability of your codebase and making your CI faster than ever before. We're also looking forward to integrating Turbo even deeper into the Vercel ecosystem. With the release of conformance and code owners, engineering organizations are shipping higher quality code faster, even as their codebases scale. Let's get into my spicy takes, because I have a lot of them. I want to start by taking a look at the repo for Turborepo. They said, 50,000 lines of Rust? So they had 70k lines of Go. Yoink. You can tell by the size of this repo that it's been through a lot of different things. Well, this is going to be a big project. This is before I've even installed anything. This is just the clone. Yeah, we're at 300 megs at 30%. Oh boy. Maybe a little under a gig, though. Let's see how big this is. 839 megs before we've even run the install commands, just for the repo. That's nuts. I want to make sure I'm not including things in dot files. Looks like they built almost everything in here, so I'm just going to blind do it. Since I haven't installed anything, it should just be the code that is relevant. And we have now, as a result of these changes, 151,000 lines of code that are Rust. Hopefully you guys are going to see the angle I'm about to take. They proudly stated they ported 70,000 lines of Go to Rust over 15 months. That means that some of the most talented engineers in the world spent a year and a half, roughly, rewriting all of their existing functionality with more than twice as much code. And they had to invent crazy techniques to do this that we've discussed here that are incredibly impressive. They're incredibly impressive. I will not downplay the quality of the engineering here at all. The issue I have is that in these 15 months, no meaningful features were shipped on Turborepo. This was time that could have been spent making Turborepo better for the users. It's setting them up for a theoretical future where it can be even more better for the users. But Go wasn't slow here. The reason they moved off of Go isn't because Rust is faster. Rust being faster is a reason that they can justify it. But the reason they moved to Rust is they wanted to move to Rust. And I don't think that was the right call. I understand, especially as a TypeScript advocate that loves type systems and the things that they enable, that Rust is something that people enjoy working in more. And having code bases that your team enjoys working in is incredibly important. This still sucks. So I pointed out that the repo also has TurboPack. Let me make sure I toss that from my check here then. That would be under crates. A really easy way to filter these out. Shift. Nice and easy. 82,000 lines. Or 86,000 lines. That's a lot less bad. I want to find an old commit. They don't squash commits, so that's going to be actually quite annoying. Let's go to the acquisition time. We'll say September of 2022. Let's pick some random day. Cool. So they turned 22,000 lines of Go code 2 years ago into 80,000 lines of Rust code today with almost no new features. This is my concern. I think Rust is a really good thing to adopt if your engineers want to adopt it and your issues are in performance, not features. But But as one of the heaviest Turborepo users, I promise you guys, there is work that needs to be done. And I'm saying this as somebody Vercel pays to show their stuff. The Turbo team has wasted an ungodly amount of time chasing the Rust Dragon. And I could be wrong saying that. I would love to see the result of faster iteration once this baseline is hit. But are we Turbo yet suggests that it's a slow grind. The fact that we're 2 years past the point where TurboPack was initially announced as the necessary solution for the next app router stuff in order for the developer experience to be good is kind of horrifying that we're not there yet still. I just a few weeks ago got TurboPack running on a pet project, not even like a real company code base. But the fact that these projects are taking this much time to get right, so when you compare to something like ESBuild, which was working minutes after it was initially announced, like contributors over time, like from it initially getting started in January to like working in April, ESBuild was good enough in its first 4 months of dev, which, like, by the way, the first month was where most of the work happened initially, and it slowed down because there wasn't too much more necessary. Despite being that early, only 4 months in a Go project, there was still enough for Evan Yu to adopt it at the same time. So in April, 4 months after ESBuild started, it was already good enough for Vite, and since then has slaughtered. Like, ESBuild won so much of this. It is also important to note that we go to the contributor graph over time, the vast majority of contributors are still Evan Wallace. But I don't know how much of that is Go versus Evan being a god and a good, solid leader here. My concern is simply that the amount of value delivered in this short window is absurd, and I've never seen that in the Rust world. In fact, it has taken the incredible Rust devs at Vercel 2+ years to even get close to this level of performance and quality that Evan Wallace had working in 4 months in Go. This is my concern. I feel like the amount of capability, experimentation, and flexibility that these devs experience in Go is exponentially better than the benefits of Rust when it comes to making something experimental. If we had a perfectly ironed out exact API that we knew exactly what we needed, then Rust would probably be a great choice. But if we're iterating on these things constantly, if we're changing what and how they work, what the inputs and outputs are expected to be, it seems pretty clear just from what I have seen that Go is the better choice. Despite not being one of my favorite languages, in fact, it's one of the ones I hate writing the most. The flexibility and agility we've seen in the Go world with ESBuild and in the Zig world with Bun seems to not even be close to matched in the Rust world, where there are a lot of projects that are trying to build useful dev tools for JavaScript devs in Rust. All of them are between 50 and 80% complete. The closest thing to a complete one is SWC, and it's still roughly where ESBuild is, not even. And that's my concern. I don't know how much value we're actually going to get from rewriting a Go project in Rust. Rewriting a JavaScript project in Rust, like rewriting Webpack, obviously massive win. But how much faster is the Rust version of Webpack actually going to be than a theoretical Go version that could have been written in 1/4 the time? And that's my issue. And this, again, isn't saying there's any issue with these engineers or the work that they've done. This is incredibly impressive and important work, but I would have liked for more time to have been spent on Turborepo, not on rewriting Turborepo. And it's going to be a while before we see the potential wins here. I'm sure the devs working on it feel much better about things overall, but I want to see real improvements to Turbo, because right now I feel like we've been maintaining the exact same experience for the better part of 2 years. And they've made better examples, they've made better things around it, but Turborepo itself has not improved for me as a user of it in quite a long time. And I think that is Rust's fault. Not Rust itself, but the introduction of Rust to the team and the code base. So those are my thoughts. I didn't want to just vaguely say this in a video and let it die, so I tweeted publicly. I specifically think Go is the right language for most JavaScript build and dev tooling. Implicitly, I'm saying not Rust, but I even explicitly say it here. Tweeting this now, for reference, in 3 years, when we realized we might have fucked up going all in on Rust. I firmly believe we went too far in the direction of Rust because the place we were in JavaScript was horrible. And build tools in JavaScript are bad. I'm not going to even pretend otherwise. But just because we're on one side of the spectrum doesn't mean jumping as hard as we can to the other side is the solution to much of anything. I think that we could have spent more time in that middle ground, and that Evan Wallace was really onto something when he started with GOLANG and ESBuild, which, if you guys aren't familiar with the history, ESBuild kickstarted this revolution in non-JavaScript based JavaScript dev tools. So hopefully, going forward, things will start moving faster, because right now, I don't think we're moving forward. I think we're moving towards Rust, and we haven't moved forward much since. I have not felt a meaningful improvement in my experience building and compiling JavaScript code since ESBuild happened 4 years ago now. We went from caring about the performance of our JavaScript tools to caring about using the perfect language for our JavaScript tools. And I don't think that shift's been for the better. I really hope we see faster progress now that most of these Rust rewrites are done. But from my experience seeing people who are even deep and excited about the Rust community and world, iteration does not tend to happen fast here. Yeah. Obligatory Elixir plug. People are asking about it in chat as a joke, but yeah, Elixir is not good at native binaries and being cross-platform, so that will not make sense here. As much as I love that language and I would love to work in Elixir-based dev tools, not going to happen for a billion reasons. Go is probably the right choice here, and you all know how much it hurts me to say that. I'd much prefer Zig, and Zig seems to be a good bet too, but this all-in bet on Rust has not been great. I think Rust makes more sense for the government than it does for JavaScript. You can read their post about why here. Future software in the US government should probably be memory safe. But JavaScript isn't. JavaScript is a messy pile of shit. And that is awesome. That's why we love JavaScript. It should be messy. It should be flexible. It should be stupid in a lot of ways. That is what JavaScript is. And Rust being so strict makes it hard to map correctly to JavaScript behaviors. And we're seeing this now. It's the same reason we can't make a good TypeScript compiler that isn't in JavaScript or TypeScript, because those behaviors are so hard to map. You might have noticed my outfit just changed. That's because I filmed that last video on stream a couple weeks ago. Since then, a couple people who were involved, both an old friend of mine who's deep in the Rust world, as well as Anthony Shu, the guy behind a lot of these Turborepo changes, reached out and gave me a ton of really interesting insights. So much so that I think it's worth another video. So if you like this one, let me know in the comments, and I'll be sure to get a follow-up out from the Rust zealots that seem to think I was wrong. Anyways, until next time, peace nerds.